Somebody has some delicious smelling coffee. Cocoa? Yummy. Does anybody have homework questions? Yeah.
It's in 4.4. It's Mindscape.
Which one? 4.4?
Yeah.
So this one, they're using super tile a little differently than we did. So you can see you can put 4 little tiles together here to make a parallelogram, or 4 triangles together to make another triangle. But when they're using super tile as the next size up that you would need to make, so you can make another parallelogram using all 9 of these tiles, and that's why we have 9. And the same for these triangles. If you put another row of 5 triangles underneath this, you would get 9 tiles. Any other questions? I sent out a reminder to bring scissors and tape, and hopefully some of you remembered. That'll make it a little easier for you today. Also, I have another reminder, study group tonight, 4 to 5. This is the last study group before our quiz next Wednesday, so I would advise you to go and get some practice with Nicholas on this work. Class is canceled on Friday, so I have a funeral to go to, so I won't be here Friday. Thank you.
One quick question. One is holding his study group the day before, the Monday before.
Oh, there is another one.
The Monday before.
Do you know what time? Is it 1 to 2 again?
Yeah.
And do you know if it's still in Wood Hall?
I believe so, yes.
So is today our review day for the quiz?
Nope, Monday will be review day.
Oh,
Yeah. Okay, so extra study group on Monday. Thank you for letting me know that.
Is the study guide up on the thing?
The study guide is still tentative. I'll have to fix that later today, so I'll try to remember. Any other questions? We're doing work in Chapter 5 now. Chapter 5 has much of its content devoted to the study of topology. So topology looks at the essential shape of an item, even if the item's distorted or stretched or shrunk. For example, a rubber band can be made to look like a square or a triangle or a circle, but it's still a rubber band, and you can't make it look like a ping pong ball or like a glove. So the study of topology is described at the bottom of the page. Topology is a mind-stretching subject that frees us from conventional geometry and allows us to appreciate geometric characteristics of objects that remain unchanged even when the objects are stretched, shrunk, distorted, or contorted. Your author calls that rubber sheet geometry, and it's quite an interesting topic. We're just looking at the section 5.2, and we started that section by taking a strip of paper and making a loop, and then we're going to examine the loop. So the life lesson in this section is to build physical models and perform experiments as a way to make new discoveries, and that's what we're going to be doing in this class. So lots of hands-on work today. Just like when you were in, did anybody take a science class where you would write in your notebook a hypothesis and then you do the experiment and write the results? That's what we're doing today. So first let's start with a loop, but we'll write in our notebooks what we're doing. 5.2, make a loop, and then we'll examine it. We're going to count the number of sides. That's what we do in our class, right? We quantify things. See if that gives us any insights. So number of sides, number of edges, and also we're going to predict what happens when you cut it down the middle. What happens when you cut it down the middle? So you can make that prediction. So we'll be making several structures today, and we'll keep track the number of sides, the number of edges, and what happens when you cut it down the middle. So for those of you with the scissors, you take a piece of paper and cut approximately an inch long strip of paper. I said an inch long, inch wide strip. Make it the long length on your paper.
Is it okay to use line paper?
Lined paper is perfect, actually. It's more flexible than the colored paper. So you would, there's a couple of pieces of paper this shape up front yet if you came in late and want to grab like 3 or 4. So we'll put a piece of tape on one end and just make a loop out of this. The markers are to help you identify how many edges and sides there are. So we'll go ahead and mark along the center, and that will help us to count the edges. So I'm just marking down the middle to count the sides, I should say. We're going to count the sides first. So I went all the way around and came back to where I started without getting on the other side because there's 2 sides to your loop. This loop is also called a cylinder, right? So the math name for that loop is a cylinder.
Wait. I thought a cylinder had to be 3-dimensional.
And a cylinder is a rectangle that's joined together on one side like this. So it's a cylinder. The number of edges, then we can look at the edges. And you can mark along one edge. You come back to where you started without touching the other edge because there's 2 edges. So you can make a prediction of what's going to happen when you cut down the middle. So I'm cutting down the red stripe that I drew, only I'm cutting more straight than I drew. Yep. I heard your prediction. I think that's a good prediction. So someone said 2 loops, and that's exactly what we got. 2 cylinders or 2 loops. So it helps if you crimp it like this, and then you can start. So squeeze it together and crimp it, and then you can start your cut. So this one was not real exciting. It's kind of boring, actually. But that's okay. We're going to do another one. If you see a scissors with black handles floating around, that's mine, and you can share them, okay? So pass them around a little bit, or maybe ask the person next to you. Well, the next one we make has a twist to it, literally. So this time we're going to make a loop with 1/2 twist. So we're going to take another one of those pieces of paper. So if you don't have any, we'll go ahead and cut one. Another band about 1 inch wide. So a rectangle about 1 inch wide, and mine are 11 inches long. So because we're cutting these up, as you form them, it's nice to put the tape in this direction on the end, not the other direction, because then we're cutting it up and you can still have tape on all the cut edge if you put it the crosswise direction. Okay. So to add the half twist, get your loop ready to go, but don't tape it yet. And once you have it in position, then flip the side over. One half twist. And it looks like that. So I'll come around and see how you're doing. Make sure you're not stuck. If you're stuck, raise your hand. It looks good. That looks good, actually. If you're stuck, yeah, make a loop. And then flip. There you go. Perfect. And you're making the plain loop yet? So that's your plain loop yet, right? Okay, so then you should untape that one and add a half twist before you connect it. Yep, perfect. This has a special name. This has a special name. Has anybody heard this, seen this before, or know what it's called? What is it called? Mobius band. Very nice, Mobius band. It shows up in sci-fi a lot. I don't know if a lot. It shows up regularly. It was in, I think, Avengers. It's in the Wheel of Time series that I'm reading now. Well, let's examine this Mobius band just like we examined the plane loop. So let's go ahead and count the number of sides. And the number of edges. So use your marker and trace along the side like we did with the plane loop, like we did with the cylinder. Okay, take your marker and plant it in the middle of your side there and just keep drawing along there. So I do these activities with my husband. Yeah, he loves them. Actually, this one he really did like. He liked it so much he did it with one of his friends. He says, "Hey, you got to see this." All right. So how many edges? How many sides does that have?
I don't.
Keep drawing. Keep drawing. Stick your pen on that marker on that paper and keep drawing along until you get back to where you started.
This line is not straight.
Yeah, it's okay if it's not straight. Yeah, there's just one side. One side. So that's really weird. We added just a half twist to the paper, and now all of a sudden instead of two sides, there's just one side. In fact, sometimes conveyor belts are made out of Mobius bands because then it wears evenly all across the whole thing because it has just one side. Well, let's go ahead and take a look at counting the number of edges. So let's take the marker and draw that along the edge. You can grab a board marker if that's easier for you to use. The nice thing about using a marker is it kind of bleeds a little bit onto both the whole edge, so you can see front and back on that edge.
Is it 2 edges?
Let's find out. I think it's 3. It's not 3. Somebody's done already? You're done already and you found one?
Yeah.
Well, you're fast. Yeah, I see I'm coming across past the other side there. So keep tracing along the edge till you get back to where you started. And you never have to go to the other side because there is only one edge. One edge. Okay, make a prediction of what's going to happen when you cut down the middle.
It's gonna be two separate. One.
So we cut the plain loop down the middle. The result was 2 loops. Make a prediction of what will happen when you cut down the red center line on this one, okay? Did I tell you the life lesson in this class, in this section? The life lesson is to build physical models and perform experiments. I think I did tell you that, didn't I? As a way to make new discoveries. So that's what we're doing.
I did it wrong. So it makes one big Mobius band.
It makes one big band. Yes, it does. It's not a Mobius band, though, because it has 2 half twists in it.
Oh.
So what you actually have is Mickey Mouse, right? You get Mickey Mouse if you do it right. So that's very, very weird. We just added a half twist to our plain loop, and now it makes completely different results when we.
What is that called? Do we just literally call it
It's called a loop with 2 half twists in it if you want to be formal. A long loop with 2 half twists. One long loop with 2 half twists. Well, that was different. Adding the half twist made a completely different result. Well, let's see what we get when we cut the edge off too. So let's make another Mobius band and cut the edge off, not the whole thing. So make another Mobius band. If you don't have a scissors and you didn't do that, you're going to need to borrow someone's scissors. So Nicholas, do you mind taking my scissors around and helping people all get a chance to make that Mobius band and cut it? Because that is your class activity for today. So go ahead and put your name placard in the picture with your Mickey Mouse, your cut Mobius band.
Like this one again?
Yep. So we're making another Mobius band. So maybe I should wait I'll wait a minute while you take your picture, okay? Yes. So this is your class activity.
This one?
Yes.
Okay.
Put your name placard there, and can you hand Nicholas the other set of scissors? Nicholas, there's an extra set up here that you can take around people too. Thank you. Okay, so get your class activity going, and then we're going to predict what happens when you just cut the edge off. What happens when you cut the edge off the Mobius band? Thank you, Nicholas. Okay, so making a second Mobius band. Okay, so you're getting ready to tape your loop together, but before you tape it, flip over half twist.
prejudice. Really, I know. So you run out of paper.
So we are going to crimp the paper and make our cut, but this time we're just cutting the edge off. Remember, it had just one edge, so we're going to cut the edge off. Being careful not to cut through, because we want to see what we get. So just cut close to the edge, about an 1/8 inch or a 1/4 inch in.
Looks like spaghetti. That's kind of cool. Like an infinity.
What is it like?
Infinity.
It's like an infinity.
I like your nails, by the way.
Thank you.
Oh,
That's so cool.
okay.
Like, who would expect that? We cut down the middle and we kept one band, one loop with 2 twists, but now we cut off the edge and we still have a Mobius band in the middle, but we have this really long skinny loop it's connected to.
Whoa, what?
So just adding that half twist, I mean, like if we took our plain loop and cut off the edge, that would have been really boring. But adding that half twist made a very different result.
So I just take a picture of this now.
So what we have is one Mobius band
I definitely did not do it right.
linked with a long loop. The long loop also has 2 half twists in it, but I'm not going to write that down, okay?
I definitely did.
So when you cut the edge off the Mobius band, you have a Mobius band looped with one long loop linked to that nice long loop. Well, if adding a half twist made that happen, let's see what happens when we add 2 half twists. Okay? I don't know. I guess it would. Let's go ahead and make 2 half twists and see if we get twice as much interesting. So now we're going to make a loop with 2 half twists. So make a loop with 2 half twists. You can predict how many numbers, the number of sides there will be. You can predict the number of edges. So we're going to make a loop with 2 half twists and count the number of sides and the number of edges.
I don't know. Mine's too thick.
So you get this lined up, ready to go. But before you put the tape attached, you make a half twist and then another half twist. So you kind of get this figure 8 shape. If you had fatter paper, it kind of makes a canoe shape.
Is it like this?
I think so. Pull it a little on the ends. Does it look like this when you do that?
I got like an
Pull with both fingers on the top or both on the bottom ones. Yeah, like that. Then I can tell it's the same, right? Yeah. So put both your thumbs on. I'm not sure yours is
Our paper just really light.
Yeah, I think you have it. I think it's just going a bit like this. Okay, let's count the number of edges and the number of sides. Here's where we get 3 edges, right? 3 sides. We'll see. Okay, so when I'm drawing on the side, I get back to where I started without getting onto the other side because there is only one side. So we're back to one side. I mean, I misspoke, didn't I? We're back to 2 sides. I drew along one side and never touched the other side because there are 2 sides. Let's check out the number of edges. Well, if you go ahead and draw a marker along that edge, you never get to the other edge because there's 2 edges. 2 edges. So when we add 1/2 twist, we create a Mobius band, which is really different from a plain loop, a plain cylinder, because it has 1 edge and 1 side. And when you cut down the middle or cut down the edge, you have these interesting results. But when you add a second 1/2 twist, so you have 2 1/2 twists, you're kind of back to where you started. Let's cut it down the middle once. Let's see if that makes anything different. Let's see what happens when we cut down the middle. So I drew a red line down the middle. I'm going to cut on that red line, kind of. So if you crimp your loop and then cut,
I'm gonna like whip out some paper at the next party I go to and just start cutting. Everyone's gonna be amazed.
That's right. That's right. You can. I'm sure you can place some bets on this. Oh, it's a terrible influence. Don't do that. Okay. So this was back to what we had at the beginning, in that there's 2 loops, but they are a little fancier loops. There are more twists in them, and they are connected. So we have 2 connected loops. So you can explore this further by making some more models at home if you'd like, with 3 1/2 twist or 4 1/2 twist, and see how the pattern continues. What we're going to do is look at identification diagrams to help to see why this is happening. So mathematicians use something called an identification diagram to describe these models. So let's look at identification diagrams. So did you ever put together a model as a child and it said put slot A in tab B, or put slot C in tab D, and then you would follow the directions. That's what identification diagrams are. So we start with a rectangle, and then we just put the directions on the rectangle of how to attach sides. So what we do is we put an arrow on each end like this to make a plain loop. Identification diagram. So the arrow shows which way to connect the two parts. So first of all, you connect the two arrows together, and you connect the two arrows in such a way that that they stay pointing the same direction. So I would connect the two arrows together, and they stay pointing the same direction, and that's my identification diagram telling me directions on how to make a plain loop or a cylinder. What if, instead of the arrows on the short sides, what if my identification diagram had the arrows on the long side? Okay, so if I have this rectangle and I have to match the arrows together in the same direction that they're facing, they have to keep facing together the same way, both to the right or both to the left. What shape is that going to give me? Can anybody picture that?
A cylinder?
Good. Yep, it's a cylinder. It's just a long, skinny cylinder. You might think of it even as a tube. Okay. So that's a cylinder as well. Actually, they're both cylinders, aren't they? Does cylinder have an A or an E?
Oh, E.
Thank you. Okay. So both times we get a cylinder when we connect the identification diagram arrows so that the arrows keep facing. Well, how are we going to describe a Mobius band then? So let's put a rectangle down, because we did start with a rectangle.
You'd have to have the arrows opposite, one up and one down.
Good job. That's exactly right. So we want the arrows to end up connecting the same way, and if they're both the same to start with, that's not going to work. So I'll put one up and one down, and I'll do that on my paper also. So I'm starting out with one up and one down, but now when I connect, you got to do it on the back side as well. So this one was pointing up. Okay, so one up and one down when I put them together, but there's one on the back, and when I flip it, then they're together. So that does describe our Mobius band. Telling which identification diagrams refer to which shape is something I'll ask you to do on a quiz. So make sure that you understand these, and hopefully our working together to make the models will help you remember how the Mobius band is constructed, and some other shapes we'll be looking at too. The identification diagram can help us figure out why we get the shapes that we do also. So what about this Mickey Mouse shape? Where did that come from? Let's use the identification diagram to explore that. So we take a Mobius band identification diagram, but I'll put 3 arrows on each side to help us visualize a little better what's going where. So there's our Mobius band again. And this one that looks like Mickey Mouse resulted from cutting the Mobius band down the center. So let's make a scissors here. Cut, 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 cut. Okay. So we're cutting our Mobius band down the center, and we're going to use this diagram to help us explore why we got the shape that we did. To do that, we use a little ladybug crawling on the paper. This whole ladybug thing really is a thing. If you look in topology books, they really do have little bugs crawling on the paper to help you visualize what's going on. So we have the ladybug crawling along here. He gets to the edge, and it's a cliff. But no, it's not a cliff because you've taped it. Where have you taped this edge? Where is the ladybug going to come out?
On the bottom.
Yep, the bottom left. Yep, very good. So this arrow was taped to this arrow when you did that little flip, and that made these arrows point the same direction when you flip them. So a ladybug comes out here, actually it'd be on the back of the paper, but on this end of the back of the paper, comes and walks along here, gets to the edge, and where does the ladybug come out? Where does this edge get taped? Yeah, top left. Yep. So these two arrows were taped together, and these two arrows were taped together. So the ladybug comes back out up here. So the ladybug's walking along the edge, but it's not an edge because you taped it. You taped this edge down to here. So the ladybug comes out on the back side of the paper down here and keeps crawling along. It comes here, and when it reaches this point has been taped up to here, so the ladybug ends up on the top left. And that's why we get this one long loop. The ladybugs traverse this twice as long as the simple piece of paper was, and we get something twice as long as that piece of paper was. And there's a half twist here and a half twist here. That gives us our Mickey Mouse ears. Well, what about if we have the Mobius band that we cut the edge off of? Let's see if we can use the identification diagram to explain why did we get this shape when we took a Mobius band and cut the edge off. We had one Mobius band and then this long piece of paper. So another Mobius band that we're going to cut. But this time we're just cutting the edge off. So we'll have scissors cutting here. And scissors cutting here. So let's let our ladybug traverse the edge and see where the ladybug is going to come out this time. So ladybug starts up here in the corner, walks along, gets to the edge, and the ladybug does not fall off the edge. Instead, the ladybug shows up over here, keeps walking along, gets to the edge, and ends up in the upper left again. So the ladybug sticking to the edge of the paper never gets in the center. And the ladybug sticking to the edge of the paper walks twice as far, twice as long as that center length. So that's why we have this edge that we cut off being twice as long as this Mobius band that's left in the middle. So the middle's never affected. We just cut off the edge and have this Mobius band remaining in the middle. See, this is a little identification diagram of a Mobius band left in the middle when you cut the edges off. And you have twice as long a cut edge with the two half twists in it. So the identification diagram can help us identify what's going on with the shape. How about if we take a shape like this? What if I take the shape that we called a tube, okay? So that was a tube, right? Well, it was really a cylinder, but it's shaped like a tube. A long cylinder. And what if I put the two ends together that are short after that? Can you picture what shape you'll have? Let's give it a try, okay? So we're going to put the long ends together. And then the double arrows on the short ends mean you put those ends together that have the double arrows. And let's go ahead and see what shape you get. Maybe you can picture it without even putting it together. That's fine too if you can. This actually works better with flimsy paper. Notebook paper is better than construction paper here. Can anybody tell what shape that's going to be? When you know, let me know. What is it? Yeah, good. It's a donut. Very good. So if you could visualize that without even putting it together, that's wonderful. Okay, so you get the tube shape from the long ends being together. And then you put the short ends together and you make a tube shape. Okay. So this is the identification diagram for an inner tube or a donut. The donut would be hollow. The math name for that is a torus. Well, this inner tube that we made, this torus, had an inside and outside yet. Okay, because you have the hollow inside of the tube of paper and you have the outside. Now, it didn't have any edges, so we made a shape with no edges, but it still had two sides. We're going to see if we can make a shape that has no edges and no sides. The identification diagram would look like this. So we're going to get away from having an edge by connecting the two long sides together and connecting the two short sides together. But you remember how we put a twist in the Mobius band? So if we can change the orientation of these ends as we connect them, so if we can have these ends upright arrows and these ends downward arrows, then when we connect those, well, then we can have just one side, not two sides, not inside and outside, just one side. So that's what your goal is to do next. So I'm going to use a piece of notebook paper cut in half. I'm going to put the identification diagram on it, and I'd like you to do that along with me, please. Okay, you have scissors? You have scissors. Who doesn't have scissors? Okay, here's one for you. And then, Nicholas, can you help share the scissors around, please, for people who get half sheets of paper? Thank you, Nicholas. Okay, so raise your hand if you need scissors, okay? So let's put the arrows on. Now when you put your arrows on this, you're going to need arrows on both sides because of the way we are flipping. So I have arrows pointing upward on the right and downward on the left. And on the other side of the paper, I want to keep that same orientation, and I can kind of see through the paper. So these were pointing upward. And these are pointing downward. So put these around pretty far down, okay? They're going to be hard to see when you're experimenting. So make sure you have plenty of arrows on these short ends. And then I'd like you to put these together so that the orientations match, so that the arrows are all oriented the same way. So these, make your tube first and then work on the short ends. Okay, so start with your tube and then work on orienting your ends so that the arrows are all pointing the same way. So mine isn't right now, right? Mine are pointing opposite ways. So see what you can do. And I'll come around and give you a hand. If you think you have it, raise your hand. If you're stuck and you need help, raise your hand.
After I get here, do I show this in?
You're going to try and roll it into a tube though if you can instead of just, you know what I mean? It's hard to do.
Do I roll it?
Oh, just a little bit. Because if you put, well, I don't know, maybe you had a different way that you're going to do it. How are you going to, well, you can roll it if you want to. That might be the
I was gonna bring it into it, but I don't know. Okay. And then I keep it.
Yeah, if you keep rolling, I think you will too. Good. Yeah, that'll work. Okay. Okay, so now just do
Okay, no, I was supposed to leave it on.
so you can mark, you can mark Oh, I think your arrows are going to have arrows on them. I think your arrows are going to match that. And we'll sit down with a good start. This can be done. Take some creativity. You put it next to each other. That's good because the arrows match, but then the ends used to have edges. So they're not really put together that. So that's a good thinking. You know, you're like thinking you're not matching, but you see how this one's coming down and that one's up. No, it is not. Well, you can see why mathematicians prefer to use rubber sheet, not paper. With the tape, could you tell how they are quite direction? I'll give you the hint. Even though you're not supposed to cut into palette, hey, you can figure it out. I'll give you a hint. You do have to cut for this one. You do have to do some cutting. The shape that you're making does not exist in 3 dimensions without cutting. So we will cut. Cut a little hole about this big, about 1.5 inches. Like that. So we're going to be studying the 4th dimension after the quiz, and at that point we'll find where this shape can exist without cutting. In 3 dimensions, we have to feed this through. We have to feed this through, and then you can connect the edges all the way around. And the edges, arrows will line up. So I saw a lot of you working to put the tubes like this and then making a half twist, which is very good thinking because that's what worked for the Mobius band, but it just doesn't work with these tubes. If you make a half twist, your arrows continue to point the same direction. But in 4 dimensions, we can make this shape without cutting, and this is called a Klein bottle. Have any of you heard of a Klein bottle before? A Klein bottle has no edges and one side. So I have a picture from your textbook of the Klein bottle. So you see that if you're an ant crawling along the edge, as you keep crawling, you remove from the, you can get along the whole edge without the whole surface. There's only one side if you're an ant crawling along that. Well, this is all we're going to do for today. I hope you enjoyed exploring some of the ideas in the Mobius band. Make sure you know how to tell the identification diagrams apart. We'll be reviewing for your quiz on Wednesday. I'll finish the review sheet later on today so you can print it out and bring to class on Monday. Monday we'll be reviewing for the Wednesday quiz.
Can we throw these away?
You can throw those away after you take a picture. Don't forget that was your class activity. So
Just
don't.
the Mobius one.
Just the Mobius
Yeah.
band was your class activity.